Good day, everyone. Today we shall be considering radioactivity, and basically we are going to be looking at calculations under this topic from past questions from different examinations. We are going to talk about terms such as half-life and decay constant. But just before we go into the calculations, let's quickly consider some important formulas that we're going to be using. And to start with, let's look at this very first one, and that is the relationship between half-life and decay constant. And half-life and decay constant, they are related with this equation. In this equation, capital letter T represents half-life, while the symbol lambda represents decay constant. So this is the relationship between half-life and decay constant. They may even ask you in some examination to state this relationship. Also, let's look at another formula that is very important here. We have another formula that is very important that we're going to be using today in today's calculations. We have n over n naught n over n naught equal to 2 raised to power minus n, and that is connected to this particular one where we have n equal to small t over capital T. Let me quickly explain this. Now, in this particular one, we have n over n naught. Now, this n that we have here, this represents the sample of a radioactive substance after some time when decay or disintegration has occurred. That is, maybe when it has decayed for some time. That is what n represents. That is the quantity of radioactive substance after decay has occurred. That is after time t. And n naught is the original quantity given at the beginning before decay will occur. And we have this small letter n representing the number of half-life in decay, and small letter t represents the time taken for a given substance to decay. Okay, let me go through it from the first equation. In the first equation, we have capital letter T, which is half-life, and half-life simply represents the time taken by half of a radioactive substance given to decay. And we also have decay constants. We also have decay constant, which is lambda, and I said decay constant and half-life, they are related with this equation. So sometimes decay constant will be given and you'll be asked to find half-life. Okay, now like I said at the beginning, we are just looking at calculation basically in this video. But if you want if you need deeper knowledge of this topic, that is every other explanation, I would recommend a book for you before the end of this video. Okay, now the second formula we're going to be considering in our calculation, we are going to look at this equal to this, and let me quickly talk about the meaning of each of these. Okay, let me start with the n naught. N naught represents the quantity of radioactive substance given before the decay. That is the meaning of n naught, the original value. While ordinary capital letter n represents the value remaining after the decay has occurred for some time, and the entire n over n naught, we call it fraction remaining after some time. That is, after the decay has occurred, the fraction that remain, that is n over n naught. And here we have small letter n that represents the number of half-life we have small letter t, which represents the time taken by decay to occur, decay time or disintegration time. Okay, now I will just add one more formula and we go straight to calculation. Okay, now the third formula we are considering, number 3, similar to number 2 but a bit different. So we have that one as n over n naught equal to exponential minus lambda t. Lambda is decay constant, t is the time for decay, while n over n naught is the fraction remaining after decay has occurred. Okay, now we are going to quickly use these formulas in solving some problems, but before we move on, if you really need you want to have deeper knowledge of this topic, you want to have every other thing that entails in this topic, I would recommend that you get this book. The name of the book is Reform Physics E-Notes, and the book has everything that you need to know in physics from grade 10 to 12, that is from SS1 to SS3, year 10 to year 12. So everything that you may need to know in every of the topic, it has at least 76 topics with detailed explanation of various examples. The book is very, very good for anyone preparing for exams such as WAEC, NECO, GCE, UTME, and even Cambridge, IGCSE, and other physics examination. And to get this, you can click on the link here to get this book. You can type this in your address bar on your website. It will take you directly to the landing page of the book and you can purchase the book there. Or if you find that difficult, you can contact this number through WhatsApp. And one of the benefits of having this book is getting a copy of this book will give you free access to at least a term, that is 3-month free online tutorial. Yes, you heard me right. 3-month free online tutorial in physics and mathematics. Yes, you will be connected to the author of the book, and in these 3 months you can ask any question. You can have a section with him, and I think that's a great opportunity. So don't hesitate to get the book, and on every topic in physics, the book is very good for you. Okay, let's go back to the classroom. Okay, now let's look at some examples on half-life and decay constant, and we will start with this very one. We are going to start with this example 1, and in this example the question says the half-life of a radioactive substance is 2 days, and what fraction will remain after 8 days. Okay, now what we have in this question, we have half-life. It is given as 2 days. According to the question, the half-life is 2 days. Okay, and they ask us what fraction will remain after 8 days. What fraction, that is fraction, remain after decay, and that represents n over n naught. That is expression representing fraction that will remain. Okay, we are looking for this, and they said after 8 days. 8 days is the time taken for the radioactive substance to decay. So that is a small letter t, decay period. Okay, now we can apply our second formula here in solving this problem. As we can see, this second formula will help us in solving this problem. That is this one in conjunction with this particular one is okay for us to solve this problem. Okay, let's see how we apply this formula in solving this problem. Okay, now you can say n over n naught equal to 2 raised to power minus n, and we'll now combine this to it to have our fraction. Okay, and we are going to start with this particular one. Remember, in the question we have a small letter t given and we have a capital letter t given, so we can easily find our n. Okay, let's quickly do that. So we can say n, which is equal to small letter t over capital letter T. In the question, what's small letter t? Small letter t is 8 days, while capital letter T is 2 days. Okay, we have 8 over 2, and mathematically this will give us 4. And going back to n over n naught, you can say this one is equal to 2 raised to power minus 4, and mathematically that will be 1 over 2 raised to power 4. And we can easily say, with what we have on the screen now, you can say n over n naught will be equal to 1 over 16, as 2 raised to power 4 equal to 16. So this is the fraction that will remain after 8 days. That is, some parts will have decayed or disintegrated or disappeared, and this is the fraction that will remain. Now another part, this is the answer to the question they ask us in this particular one. Okay, now another thing they may ask in some of this, as you can see from the example we are treating, the question is from UTME past question. You can see it's UTME question, year 2022, question 8. Now another thing they may ask in this question, they ask for the fraction that will remain. Okay, in some questions they will say the fraction that will have disintegrated or the fraction that will have decayed. That may be the question, and if that is the question, it's very, very simple. After you will have calculated the fraction that will remain, the fraction that will have disintegrated is a very, very simple fraction that will have decay. Let me just put it there, fraction that has decay is very, very simple. You can just, since you've calculated the fraction that remain, fraction that decay is 1 minus fraction that remain mathematically. So you can note this, though this is not what the question asked us to calculate. We found what we are asked to find there, but I'm just adding this, that in case the question says fraction that has decayed, you can just use 1 minus n over n naught and you will get that. And in this case, that will be 1 minus 1 over 16. And definitely that will give us 15 over 16 mathematically, if that is the question. Okay, without wasting our time, let's move away from here. Let's look at another example. Okay, let's consider another example. Let's go straight to this, and this will be about example 2. Don't just mind the numbering. This will be our example 2 because we've skipped one particular example. And in this particular one, we have a sample of radioactive substance which is found to be left with 1 over 32 of its original initial count rate after 110 years. We have to calculate the decay constant. Now, what are the parameters in this question? You can see the question is from WAEC 2015, question number 12D. Now, what are the parameters given to us here? Number 1, we have the fraction that is left after 110 years. So the fraction that is left is n over n naught, and is equal to 1 over 32. And after how many years, which is a small letter t, after 110 years. And here half-life is not given, we may not really need it. We have asked to find a decay constant. Okay, using one of the formulas that I gave at the beginning of the video, we can consider using this n over n naught equal to exponential minus lambda t. And we can as well use our n over n naught equal to 2 raised to the power minus n, and it will take us to, in that one we just get our half-life and use half-life to find the decay constant, but we can easily use this one as well. Okay, according to the question, n over n naught is 1 over 32. Okay, now we can say 1 over 32 will be equal to exponential minus lambda, and t is given as 110 in this question. Okay, we are looking for lambda, and mathematically when you have an expression like this, that is when you have an equation in this form, you can easily resolve it to something that appear like this. You can have ln 1 minus ln 32, and that will be equal to minus 110 lambda. Mathematically, I want to believe you will have done something similar to this in your further mathematics or general mathematics. So when you have an expression like this, you can easily resolve it to something like this. We may say we've eliminated the exponential function and we're having a limit function or logarithm function here. Okay, now from here you can just pick up your calculator and just press the values of this from your calculator. Now from what we have, ln 1 minus ln 32 on your calculator, you can press it direct. The 1 and minus ln 32 on your calculator will give you minus 3.4657 on your calculator. That is ln 1 minus ln 32. That is what it will give you. Okay, and that is equal to minus 110 lambda, and we know that the minus will cancel minus, and lambda will be equal to 3.4657 over 110, and that will give us lambda to be equal to 0.0315 per year. That's the unit here, because the time given is in years, so this will be per year. Okay, now this how you attempt this question, we've been able to use one of our formula again. Let me write this one properly. Okay, now this is a question from WAEC Past question 2015 question 12D. Okay, you can see how we are able to solve this. You can see the given parameters and what we were able to do here. Okay, all right, we are going to go straight to another example. Let's consider example 4. But if you are watching this video and you are yet to subscribe to this channel, please do subscribe to the channel, and also click on notification button so that whenever a video like this is released, you'll get a notification. And probably when we're having our live session as well, you'll be notified to be part of the live class. Okay, let's move straight to question number example number 4, excuse me. And also, if any of this video has added any value to you, please drop a comment at the comment section. Let's know how you feel and give us a thumbs up. And if at all you want us to correct something, you can as well drop it at the comment section. We'll work on it. Okay, example number 4, we have a question here that says in 24 days a radioactive isotope decrease in mass from 128 gram to 2 gram. what is the half-life of the radioactive material. This one is coming from NECO 2021. And okay, what we have here, basically we have 24 days, which is decay time. 24 days is the decay time, and we have a radioactive isotope that decreased from mass of 128 to 2 grams now, which means our original mass of the radioactive substance, which is N0, is 128 according to the question, while the mass after 24 days, that is after decay, the mass after decay, which is 24 days period, is 2 grams. Now we have to find the half-life of this. Okay, now to do that, we can easily use any of our formulas. Okay, let's go with n over n naught equal to 2 raised to power minus n to first find the number of our half-life, and that will be equal to 2 over 128 equal to 2 raised to power, okay, let me just go straight by saying 1 over 2 raised to power n. Okay, from this one, 2 over 128 will definitely give us 1 over 64, and that will be equal to 1 over 2 raised to power n. And 1 over 64 in terms of power of 2 will be equal to 1 over 2 raised to power 6, and that will be equal, because 64 is 2 raised to power 6, you can check that on your calculator, and that will be equal to 1 over 2 raised to power n. Mathematically, comparing both sides of this equation, we can say our n equal to 6, and if our n is equal to 6, we can easily say, remember, n equal to small letter t over capital letter T. But we are looking for capital letter T. We can make capital letter T the subject of the formula by saying small letter t over n. Our n is 6. What's the value of our small letter t according to the question? Our small letter t according to the question is 24 days. So let's just bring it into this equation by saying capital letter T will be equal to 24 over n, small letter n, which is 6, and our half-life will be equal to 4 days. I want to believe this is very clear, but in case you have any question, please go straight to the comment section and just drop your question. Or if you have any addition or any very good suggestion, please feel free to drop them at the comment section. And if you love the way the video is, please give us thumbs up and also say something at the comment section. And also, if you are watching this video, you are yet to subscribe to the channel, please do subscribe to the channel so that you can get a video as soon as we are dropping them. Okay, we move straight to the next example because of our time. We move straight to the next example, and the next example will be on the next page. Okay, let's consider the example on the next page. Okay, now in this particular one, question number 5 says, given that decay constant of radioactive element is 0.055 per seconds, we have to calculate the half-life. Okay, according to the question, what we're given here is decay constant. Decay constant is given as 0.055 per seconds, and we have to find the half-life of this. Now remember, at the beginning I give some formula. This one is one of them. Half-life equal to 0.693 over decay constant. So, and if that is the case, we can easily find our half-life here by saying half-life will be equal to 0.693 over the value of the decay constant given to us in the question, which is 0.055, 0.055, 0.055. and the value of half-life will be equal to, if you press your calculator, the value of half-life will be equal to 12.6 seconds. 12.6 seconds. That will be the value of half-life if you press your calculator. And that's as simple as that. Let's move to the next example because of our time. And this particular one is coming from UTME year 2020 question 27. Okay, now let's go to the next example. Example 6 is also from UTME 2009 question 47, and the question says a piece of radioactive material contains 10 raised to power 20 atoms. Please don't mind this. Let me just quickly correct this. Let me quickly correct this one. So that is what we're supposed to have there. Okay. Now, what the question is saying, that we have a piece of radioactive material that contains 10 raised to power 20 atoms. That is the initial count rate, or the original value given, N naught equal to 10 raised to power 20. Let me just put it in the normal way here. 10 raised to power 20 atoms. That's the original value of the radioactive substance. And we have half-life of that radioactive substance given in the question as 20 seconds. Okay, they now ask us to find the number of disintegration in the first seconds. Number of disintegration in the first seconds. Let's see how we can quickly find this. Now, another word to use for this expression, we can call it activities in the first seconds. Okay, activities in the first seconds. Let's represent activities with A naught. Okay, now the simple formula for this, though there are two ways to approach this, but the simplest way to approach this is to use this formula: A naught equal to lambda N naught. This is the simplest formula you can use in finding this. First thing we just need to do here is to find our lambda, and remember that lambda equal to 0.693 over half-life, and half-life is given as 20, which means our lambda will be equal to, if you press your calculator here, our lambda will be equal to 0.03465. That will be the value of our lambda. You press your calculator with what we have here. Okay, and to substitute this into the formula, we are going to have our A naught to be equal to, remember, A naught equal to lambda N naught, so that will be 0.03465 multiplied by 10 raised to power 20, which means our activities in the first seconds will be equal to 3.465 times 10 raised to power 18. That's the answer to that question. Atoms. That is our activities. That is according to the question, they call it the number of disintegration in the first seconds, and this one is coming from UTME 2009 question 47. So you can easily arrive at the answer like this, but there's another method you can as well use, though it's a bit long. You can just consider using this formula. First thing you just need to do is find the value of n, which is the value remaining after 1 second. So by saying n naught exponential minus lambda t, you can use this formula. Remember, this is coming from n over n naught equal to exponential minus lambda t. That is, you are making n the square root of the formula. That's why you have this particular one. Okay, That's why we have this particular one. And after finding the value of your n using this formula, you can now see the number of discrete integration in the first second will be equal to n naught, which is original value given, minus factor remaining in the first seconds. And remember here, t will be equal to 1 seconds. You can also use this formula and you arrive at the same answer as well. Okay, that is the alternative method, but it's a bit longer than the method that we use, but you can check it out. You're going to arrive at the same answer. And lastly, we want to, okay, let's consider the next example here. Let's consider the next example, which is example number 7. Let's consider this example number 7. In this particular one, we have uranium with mass and atomic number 235 and 92. That is, we have uranium is U. It has atomic mass number of 235. That's number of 235 and atomic number 92. Okay, now according to the question, this uranium decays by emitting 2 alpha particles. And we all know that when an atom decays by emitting alpha particle, it means the mass number will reduce by 4, while the atomic number reduced by 2. But in this question, it emits 2 alpha particles. So we are going to have something like this. So in this one, this represents the alpha particle, while according to the question, it emits 2 alpha particles. That's why we have that 2 in front of it. And it also emits 3 beta particles. Okay, when an atom emits beta particles, the atomic number will remain, the mass number will remain unchanged, while the atomic number will increase by 1. And we can have that one in this form. This represents a beta particle. So in this expression, this one represents a beta particle. According to the question, it emits 3 beta particles. Okay, and a gamma ray. When an atom emits gamma ray, both mass number and atomic number remain unchanged. With that, we are going to have this and this remaining unchanged. And they want us to find the mass and atomic number of the resulting element. Which element will it form? Okay, very simple. The element that it will form, to do that we are going to easily find, sorry for that, to make that one clearer. Okay, now to do that, let's just represent the element that will be formed with a symbol. Let's say we have it as symbol Z, and the mass number will be B, while the atomic number will be A. Okay, now when you have something like this, what you just need to do is balance the mass number on both sides of the equation and atomic number on both sides of the equation. Now you can see on both sides of the equation, we have mass number 235 here, and we have all the numbers at the top here as mass number, so we can equate them to each other. Now mathematically, you can easily say your 235 will be equal to 2 multiplied by 4, that is the mass number here multiplied by these 2. Okay, now plus 3 multiplied by 0 plus 0 plus plus b rather. As you can see, what we have here is B, right? This is what we have here. Okay, and with this, you can easily say B will be equal to 235 minus 8, and that will be equal to 235 minus 8 will give us a 227. So it means the mass number of the element form is 227. Similarly, we can do that to the atomic number aspect. Okay, let's equate all the atomic number as well. So you can say 92 equal to 2 times 2 plus 3 multiplied by minus 1. We're considering the atomic number now, plus 0 plus A. Let me show you what is happening here. That is, we are considering the atomic number aspect, including that part of A as well. So that is what we combine together. We are just equating the atomic number on both sides of this equation. Okay, and in doing this, we are going to have 92 equal to 4 minus 3 plus A. So A would definitely be equal to 92 minus 1, and atomic number of the element that will be formed will be equal to 91. So the new element form, which is said BA, will be equal to, that is 227 and 91. So we have a 22791 as the new element formed. So that is how you solve this. Let me briefly summarize what is happening here. When radioactive substance decay, it will do that by emitting either alpha, beta, or gamma radiation, alpha particle, beta particle, or gamma radiation. And it is possible for a particular element to emit the 3 of them in succession. It is possible, like in this case, this one emitted 2 alpha particles, 3 beta particles, and 1 gamma ray. So that is what they ask us to solve here. And when an element emits alpha particle, the mass number will reduce by 4, and the atomic number will reduce by 2 to form another element. When element emits beta particle, the mass number remains unchanged, while the atomic number will increase by 1. It will also form another element. But when element emits gamma radiation, nothing will change in the element, because the mass numbers will still remain the way it is, and the atomic number remain the way it is. Okay, but if any part of this video is not really clear to you, please feel free to go to the comment section and let me know at the comment section. And if by now you are yet to subscribe to the channel, please quickly do that and click on notification button, so that when we have new video, you get a notification, or when we have in our live section. And please give us thumbs up if you love our video. And before I go, I told you at the beginning of this video that I'm going to just talk about the calculation on radioactivities, and I have a note compiled for grade 10 to 12, that is year 10 to 12 students in SS1 to 3 in physics, on all the 76 topics. And this note covers curriculums such as WAEC, NECO, GCE, UTME, and IGCSE. So if you just really want to have a very good knowledge of physics, even if you don't have any note right from SS1 and you are preparing for any examination, or probably you are just in SS1 and you want to have this note to be a reference material with any note that will be given in your school, feel free to go to this, type this address in your address bar in your browser, and you'll be directed to this note. It's just at a token. You get it at a token. If you're finding it difficult to do that, just contact me on this WhatsApp number. And doing that, getting a copy of this note will make you to have an access to at least a term free online tutorial in physics and mathematics. That is complete term, a duration of 3 months to have an online tutorial in physics and mathematics with the author of this book. You are free. Once you get a copy of this note, what you just need is to contact the number on the screen, and you'll be added to the class. Some people are already enjoying it already. Some are enjoying it already. So once you have a copy of this note, contact the WhatsApp number on this screen, and you'll be added to the class. And whenever we have a live section, you'll be part of it. Okay. We want you to also practice these 3 questions. Please feel free to drop your answer at the comment section, and if any of them is difficult, just let me know. I will provide a solution to any of the questions that is difficult. Feel free to drop your answer at the comment section. Practice these 3 questions. They cut across what we've discussed so far today, and if you have any other question, please feel free to drop it at the comment section, and it will be attended to. Thanks for being the part of today's class. Thank you, and God bless you.